Hello everyone. Today we will look at two popular techniques of visualizing high-dimensional data. Usually as engineers or statisticians, we have to handle datasets where the data points have a large number of features. This could be in the order of dozens of features, for example, if we are collecting the grades of the students at the university, or thousands of features if we are collecting the color values of each pixel in a high-definition image. We need these visualization techniques so that we have a feeling of how the data is arranged in data space, and so that we learn a bit about their similarities and disparities, thus allowing us, for example, to develop effective machine learning algorithms. These two algorithms that we are going to look at today are PCA for Principal Component Analysis and t-SNE for T-distributed stochastic neighbor embedding. The short lecture, which will give an introduction and an overview of these two techniques, will be complemented by a lecture on the mathematical analysis of these two algorithms, then a practical tutorial where we learn how to practically and effectively implement these two algorithms. Let's begin. We start with the Principal Component Analysis algorithm, PCA. This is an old but very popular technique that is first and foremost a dimension reduction technique. This means that if you have a data set where you have thousands of features, you can use PCA to reduce the number of features to an arbitrary low number, let's say hundreds of features or like 15 features. And the way it does this is by linearly mapping the high dimensional objects to lower dimensional objects using an orthogonal projection. And if you choose the lower dimension to be 1, 2, or 3, then you can exploit PCA to visualize your data by visualizing the lower dimensional objects that are projections of the higher dimensional objects. More formally, we have a data set where we have a certain number of points. Here we have n points, where each point has a large number of features, here denoted by small n. And what we want to do is to project this data onto a lower dimensional space, let's say of dimension k. In other words, we have to find vectors u1, u2, up to uk that would span this vector space so that we can project our data and obtain lower dimensional objects. And the criterion for choosing this projection vector space is to minimize the projection error, which is simply defined as being the sum of the squares of the distances between your original high dimensional data and their lower dimensional projections. The solution to the problem posed by the PCA can be described in three fairly simple steps. And in the next lecture, we will see a mathematical proof of this. The first step is to compute what we call the covariance matrix of the data, which is an average of products of data points by their transpose. This covariance matrix gives us an overview on the statistical properties of the features. It estimates the variance of each feature, but also estimates the correlation between different features. In the next step, we use a linear algebra result that tells us that if we want to reduce the rank of sigma while keeping most of the information contained in this matrix sigma, we have to apply a singular value decomposition, SVD, on sigma to compute its eigenvalues and eigenvectors. If we take the k largest eigenvalues and the corresponding k eigenvectors u1, u2, up to uk, we get those price directions that define the lower dimensional vector space on which we want to project our high dimensional data. Then we collect the coordinates of these directions in a matrix UK that will be key in our third and final step of the algorithm, where we take our high dimensional data, then multiply it by the projection matrix UK to obtain those low dimensional vectors yi that we can then use either to analyze the high dimensional data set xi or to speed up a machine learning algorithm running on that data set, or to simply visualize the data if the low dimension k is smaller than 3. So let's try and apply PCA to a first practical problem. Let's say that some botanists provided us with a set of measurements concerning different types of irises. Each row in this table has the features of our data points. These measurements concern the length and the width of sepals and petals. Therefore, our data is four-dimensional. We're not specialists in botany, but as engineers and statisticians, we should try and analyze this data. And a good starting point is to try and visualize it using PCA. So we can, for example, reduce the number of features to 2. And to help us decide whether the patterns that we will observe make sense, the botanists provided us with the type of irises corresponding to each set of measurements, so we can have setosas, versicolors, or virginicas. And we see here that we can easily detect the clusters corresponding to the types of irises by applying this two-dimensional PCA, already by projection onto the first direction provided by PCA. We see that the setosas cluster away from the other two types of irises. By adding the second direction provided by PCA, we are able to get a two-dimensional image where we can easily distinguish the versicolors from the virginicas. Therefore, we see that visualization using PCA can help us detect patterns in data about which we have no prior knowledge. So let us look at a second example where we try to visualize high-dimensional data using PCA. Here we have 8 pixel by 8 pixel images of handwritten digits. So we can represent the data as 8 by 8 matrices. So the data is 64-dimensional. And the entries of these matrices are values between 0 and 1 corresponding to the brightness of each pixel. Again, we will try to visualize this data in 2 dimensions, and we'll use PCA for that. And here is the result by PCA, which is a scatter plot in which we are not able to distinguish any clusters like we did previously. And the reason for that is that in its first step, PCA analyzes the covariance matrix of the data and tries to explain the data by looking at just the variance. And here we're in the situation where we cannot do that. So let us color the dots to recognize the digits they correspond to. And we can see that the PCA actually did a very good job in separating the 4s from, for example, here, the 2s. And the reason for this is that when you compare images of 4s and 2s, pixel by pixel, there's a large variance. However, when you look, for example, at the light blue dots and the yellow dots, which correspond to 8 and 9, PCA did a very poor job in separating these two because there is little variance between images of 8s and 9s. Here we see one of the main characteristics of PCA, which is not always helpful when visualizing high-dimensional data. It maximizes the variance of the projected data. By looking for the low-dimensional vector space that minimizes the projection error, PCA ensures that if two high-dimensional objects are far from each other, then their lower dimensional projections are also far from each other. This, combined with the fact that PCA is a linear projection technique, implies that it cannot extract non-linear structures, meaning that if your data lives on a low-dimensional, non-flat manifold, which is the case in many applications, it will fail to see this, and it will consider your object as living in a high-dimensional, flat vector space. In this example, the data lies on a two-dimensional manifold called the Swiss roll, which you can imagine as being a sheet of paper rolled in this manner. PCA will fail to see this as a two-dimensional sheet of paper and will see it as a fully three-dimensional object. It will suggest to project the data on this direction because it maximizes the variance and preserves the large distances. As a consequence, the red points will be projected on the blue points. Another way to see this is that PCA measures the distance between the red points and the blue points in the three-dimensional Euclidean distance. It will see that this distance is small compared to the other distances in your dataset, and therefore it is okay to project them on top of each other. A better way to measure the distance in these examples is to take the geodesic distance, meaning that you measure the length of the shortest curve that goes along the sheet of paper and connects the blue points to the red points. And here we see that this distance is very large. A better way to study this example is to use t-SNE, t-distributed stochastic neighbor embedding. This is a non-linear projection technique that has the following priority rule. If your high-dimensional objects are close to each other, then their lower dimensional representations must be close to each other, while it is perfectly okay to distort the large distances. So how does the t-SNE algorithm work in practice? Here we will see a very simplified version of this algorithm, and in the practical tutorial, we will see a refined version of the t-SNE algorithm. In the next lecture, we will try to mathematically justify that the t-SNE algorithm does what it claims to do. The first building block of the t-SNE algorithm is to measure the similarities between the high-dimensional points as probabilities. So to every pair of points xi, xj, we assign a probability pij. In the numerator, you recognize the Gaussian distribution density function, and the denominator is just a normalizing factor so that the pij's sum up to 1. And this is indeed a measure of the similarity between the points, because when xi and xj are close to each other, the numerator is almost equal to 1. But when they are far from each other, this probability will tend to 0. We can do a similar thing in the lower dimensional space, meaning to every pair of points yi, yj, which play the role of the lower dimensional representations of the points xi, xj, we can assign a measure of the similarity qij, but this time we will use the Cauchy distribution density function. And the Cauchy distribution is a special case of the student t distribution, and this is where the t in t-SNE comes from. And this is again a measure of the similarity between the points. Now we can collect all the probabilities pij to define a probability measure p, and we can do the same thing in the lower dimensional space and define a probability q. And we can measure the similarity of q to p using what we call the Coolback-Liblar divergence, which is given by this formula. Notice that this divergence is equal to 0 when q is equal to p. But we cannot necessarily have q equal to p because we are using different density functions. So what we do is to randomly initialize the yi's, which will define for us the qij's, which will give us a value for the Coolback-Liblar divergence. Then we start moving the yi's in the lower dimensional space, forcing those qij's to change, forcing the Coolback-Liblar divergence to change. How do we move the yi's? We do that by trying to minimize this Coolback-Liblar divergence. And for that, we can use, for example, the stochastic gradient descent algorithm. At the end of the algorithm, what will happen is that if xi and xj are close to each other, then yi and yj will be forced to be close to each other. But if xi and xj are far from each other, yi and yj will be allowed to be even further apart from each other. As a practical example, we apply t-SNE to the dataset of handwritten digits. Here, we see very well separated clusters, which is usually good when trying to visualize high-dimensional data. When we add the colors to the plot, we see that these clusters actually make sense, with some abnormalities that can be easily explained. For example, we see here that someone might have written their 5 like a 6. This sounds like a very nice story about t-SNE, but this algorithm is not without its issues. First, different iterations of the algorithm may produce different outcomes. And one of the reasons for this is that we are trying to minimize a non-convex function using a random initialization, and depending on where we start, we may end up with a different solution. This is in contrast to PCA, which always gives the same solution. Second, You must not read anything into the cluster sizes, shapes, and positions provided by t-SNE. t-SNE is purely for visualization, and the geometric configuration we get is one among many others that locally satisfies certain constraints. As such, we must not build on top of t-SNE in our machine learning algorithms. And again, this is not the case for PCA. Finally, t-SNE is computationally expensive. And the main reason for this is that at every iteration of the thousands of iterations of the gradient descent algorithm, we must compute the probabilities Qij's for every pair of points in our dataset. What we do in practice is that we first reduce the number of features in our high-dimensional dataset using PCA, then apply t-SNE to visualize the lower dimensional dataset. These remarks conclude our lecture for today. Thank you very much for your attention.